All right, it is. It's 107. Today is 129/21. This is day 3 of the lecture. You know, we do 1, 2, 3, and we hit the test. Fortunately, it's the weekend for you. So, what I'm going to do for Monday is when you come in at 1, for Alpha members that come in at 1, and my internet's acting up a little bit. All right, now we're working again. All right, when you come in Monday at 1, we will have a review first. Okay, I'll do a little review because it's the weekend. So the Alpha group come in at 1, not 1:30, not 1:45. Be here at 1 o'clock. We will review for the first hour. Okay, from 1 to 2, we will review. And then I'll open up the test at 2 and let you take it. Okay, so at 1 o'clock on Monday, I'm adding a little bit of review to it since it's the weekend. And we'll be able to ask me questions, go over any of the homework. If you want to do a couple of practice ABGs or anything else, don't forget, this is not just ABGs. It's a lot of information. As you can see behind me, today we're going to talk about carbon dioxide transport. It's a little more involved than oxygen, okay? And so these are the things you want to learn and know, how CO2 is transported in the blood. And so Monday, what I'll do is for the Alpha group, at 1 o'clock, we'll come in. I'm starting at 1. I'm not waiting till 1:15, and I'm going to start doing some reviewing, okay? And then you can ask me questions, and at 2 o'clock, you're going to clear your desk and take the test, all right? And then when my Alpha group comes in, my Omega group come in at 4, well, then you come in at 4, and we will review from 4 to 5. Then I will allow you to take your exam at 5 o'clock, okay? And that'll give us a little bit of review, a little bit of extra pull before you take the test, since it's going to be the weekend, all right? Since it's going to be the weekend coming up. But during the weekend, you need to look at these lectures, do your reading. I'm going to give you a couple of workbook pages to do to make sure you're in that workbook and in that Egan's book, okay? It's going to be some workbook stuff for homework over the weekend. All right, so let's get started. First, we're going to start off, like I said, with homework number 3. Homework number 3. For those who had questions on homework number 3, we'll work out a few of those. Try to keep it stay low so it'll be easier for you to see. Yeah, I'm all right, and then move out the way. All right, so all right. So homework number 3 said, answer the following questions. You must show your work, of course, but answer these questions. This is going to combining what you've learned, the amount of oxygen that is dissolved in the plasma, the combined O2, the total oxygen content, the alveolar oxygen tension, and the AA gradient. That's what they're asking from a set of given parameters that they gave you, okay? For instance, I'm going to do number 1. Now, so the given is a hemoglobin of 11, a P little a O2 of 58, a SaO2, which is the SAT, is 97%. The respiratory quotient is 1. They are on 40% FiO2. Barometric pressure 760. Their P little a CO2 is 40. With those given parameters, they want you to tell them the dissolved amount, tell them the combined amount, tell them the total O2 amount, the P big AO2, and the AA gradient. Okay? You got to know these down pat. So let's do one at a time. So for dissolved oxygen, dissolved is 0.003 times the P little a O2. That is the formula for dissolve. All right. So knowing that, we got 0.003 times a P little a O2 of 58. All right. So 0.003 times 58 is 0.174 mL. That is the amount dissolved. That is the amount dissolved. So dissolved was DISS was 0.174 mL. The next one wants to know the combined. Combined to hemoglobin, right? Okay, let's look at it. Combined to hemoglobin is 1.34 times the hemoglobin times the SAT, or the SaO2. That is the formula. So we have 1.34 times the hemoglobin in this problem is 11 times the SAT, which is 97%, but remember it's as a decimal. So 0.97. Let me let Sydney in while we're doing these. All right. So now we just simply multiply. They're all in parentheses. It's all, it doesn't matter what you do first. So 1.34 times 11 times 0.97. That is 14.29. So let's just say 14.3 volumes percent. Sometimes they say grams percent. Either one, you may see it grams percent, or you may see it as volumes percent. That's how much is combined to the hemoglobin. So that one is 14.3 volume percent. No, you don't have to. You can round to the nearest. But I'm not looking for exact, it's not going to be like one that says you should have put 0.77356622. Right? Nobody going to do all that. Just whatever, your choices are going to be obvious. Okay?
Is that going to be the same thing for the total O2 content? Is going to be a volume percent or grams?
It's volume percent. Yeah, volume percent. All right, so the next one is total. Total is written as C(a)O2. That's the total O2 content. The C(a)O2 is 0.003 times P(a)O2, right? Plus 1.34 times hemoglobin times SAT. Just adding those two together. Well, we know our dissolved amount is 0.174 plus our combined amount was 14.3. And so we do that. We say 0.174 plus 14.3, and that gives us about 14.5 volumes percent. So the total O2 content of this person here is 14.5 volumes percent. Now, what we learned for what we will continue to talk about is that this is mildly hypoxic when it comes to volumes percent. Remember, we learned what hypoxic is with the P little AO2 was 79 to 60, I believe, and then 59 to 40 was moderate, and then anything less than 40 was severe. But I told you, there's other ways to tell if you are hypoxic, right? And I said the other way would be for looking at the volumes percent. All right, so let's look at it right quick. Where is it at? Volumes percent for the hypoxia part. Hold on. There it is. All right, so we're looking at hypoxemia. If I'm looking with the P little AO2, 80 to 100 is normal, right? That's in part of your ABG. Okay, that's the oxygenation status of your ABG. Don't forget the ABG has either acid-base status and it has a oxygenation status, two separate trees. One has ventilation apples and the other one has oxygenation apples. They are not the same tree. Okay, so we looked and learned what mild hypoxemia was. If you have that at 79 to 60 is mild, 59 to 40 is moderate, and less than 40, any P little a O2 less than 40 is severe. Now 40 is not severe. Less than 40 is severe, right? All right, so let's look at the oxygen content. It also will tell us what's mild, moderate, or severe hypoxemia. All right, look at the O2 content, total O2 content. Normal is 18 to 20 volumes percent. 18 to 20 volumes percent. Mild hypoxemia would be 15 to 17 volumes percent. Moderate is 12 to 14 volumes percent. And then severe hypoxemia is anything less than 12 volumes percent. So looking at our answer for total O2 content was 14.5. So you could say 15, right? Or about that. So this person is suffering from what? Mild hypoxemia, or you could say moderate if you just go by 14.5 because we already rounded to get to 5. So about moderate hypoxemia, where you look at it and say, well, damn, his oxygen saturation in this problem, and plus they just give you some numbers, right? And not necessarily mean this holds true to a human, right? Because if his oxygen saturation is 97%, you wouldn't say he was moderately hypoxic, but this is a closer look. What would be the reason from what you're given would say this is probably why he's moderately hypoxic? There's one thing that would be the cause of this whole thing, because his sat is fine. But what parameter that they give you in the problem? The parameter.
Is hemoglobin?
Huh?
Hemoglobin?
Say it again.
Hemoglobin?
Hemoglobin. Because our hemoglobin is supposed to be 12 to 15 grams, right? And his hemoglobin is only 11. So it's a little low. So if your hemoglobin is a little low, it stands to reason you will be a mildly hypoxic or could be severe or whatever, because hemoglobin is what carries what?
Oxygen.
Oxygen. So if you don't have the hemoglobin, you don't have the oxygen, right? All right. That's just kind of where you want to be for each one. If it's 17, that's just like a midway point. All right, so let's keep on looking at it. Good, so that's a good inference. It's because it's how his hemoglobin. The lower the hemoglobin, the lower the total O2 content is going to be, because you multiply the hemoglobin, right? So if it's only 8 or 9, it's going to be low. It's going to make everything low, okay? So what this is saying is that SAT being 97, guys, is that it's saying that out of those low hemoglobin, those 11 hemoglobin are still 97% saturated, even though it's less of them, okay? It's kind of like having a bus. If you have a bus that holds 100 people and it's 100 people on it, it's full, right? It's 100% full. But what if you now have a bus, the short bus, that only has 10 seats? But if it's 10 people on there, they're still considered 100% full, right? It's full, but it's still not as many as the big bus, right? Still way less than the big bus. Okay, so you have to look at it in percents, like, you know, as a whole. I forgot what word I'm trying to say. But you know what I'm saying. All right. So let's keep going. Then they ask us the P big A O2. All right. So P big A O2 equals FiO2 times the P bar minus the pressure of water minus the P little a CO2 divided by the RQ. All right, so using the parameters that they give us, let me see something. Maria, are you with me? Maria? Did you get my email, Maria, about that question you asked me?
Yes.
Okay, I think you said yeah, but I'm not sure. But okay. Well, make sure you understand that the CO2 is not the same as the water pressure. Okay, water pressure's normal value is 47 millimeters of mercury. Okay, that's water pressure. All right, so knowing what we know, let's see here. So P big A O2 equals FiO2. How much oxygen are they on? 40%. So that's 0.4 times the P bar in this case is 760 minus, did they give us a water pressure? So we use what? 47 minus, what's the CO2? 40 divided by the RQ of 1. All right, so we do what's in parentheses first. This is 713 times 0.4 minus 40. 40 divided by 1 is 40. All right. So 0.4 times 713 is 285.2 minus 40. So you have a P big A O2 of 245.2 millimeters of mercury. So I'll write it over here. The P big A O2 ended up being 245.2 millimeters of mercury. And then lastly, they want to know the AA gradient.
I just have one question.
Yeah. Yeah.
Okay, so you know how it's P big A minus little a, but the O2 is on the outside of the parentheses?
Yeah.
So are we still supposed to, after we subtract that in the middle, are we still supposed to times that by
No, that's just
FiO2?
that word is simply that, it's just abbreviation.
Okay.
Just like P little a CO2, this is just abbreviation.
Okay.
They're just showing you that they want you to subtract alveolar pressure from the arterial.
That's what I did. I just didn't know if maybe we were supposed to put that
No, it's not part of it. It's not a formula. It's just
Okay.
simply an abbreviation. AA gradient is big A minus little a O2. This is what this is saying is the pressure of alveolar oxygen minus arterial oxygen. Alveolar minus arterial oxygen. That's all it's saying. Okay? Now, we know that the big A is 245.2 millimeters of mercury minus, what is the little a? P little AO2 was what? Huh?
58.
All right. So when we subtract that, we have 245 minus 58. Minus 58.
187.2
So
millimeters of mercury.
A gradient is 150. What would you say? 187. 187.2 millimeters of mercury. So that's a pressure now. So my A gradient, 187.2 millimeters of mercury. And that's what they wanted you to do for all of these. Just use what they give you, plug it into the correct formula, and that's how we go.
Mr. McCarthy, for the gradient, all you do is subtract those two. You don't multiply anything.
Yep, that's it.
Okay.
AA gradient, all they want you to do is subtract the arterial oxygen away from the alveolar oxygen.
Okay.
All they want you to do. All right, so that was number one. And they're all the same. So if you didn't know what you did on one number, now you saw how it was done, we can move on unless there's a particular one that you need to see. But they all the same. You just gotta have the right process, make sure you're using the right formula, and just calculate. But if you need to see one, you let me know, we'll do it. All right, everybody good on that. What was the other homework? That's it? Okay, good. All right, so let's move right along. Now, we're going to finish watching that video. I don't know if you watched it last night, but we're going to watch it again and kind of stop here and there until the break, and then we'll take a break and come back from break and go into CO2 transport. So if you're watching me later on today, I can't record the YouTube part, so you'll have to watch it on your own. But that's why we want everybody to be participating here live. All right. So I'm going to pause the recording, and then I'm going to play the video, and then we'll come back after break. All right. So hold on. Before we go into the compensation component of the video, I want to reiterate on something. Remember I told you, what if you have this? What if you have a pH of 7.1, a CO2 of 65, a Bicarb of 10, right? And a P little AO2 of 100, okay? What is pH doing?
Acid.
Acid. So we are in the acidosis. All right, let's see what's CO2 doing?
Acid.
Acid. What's Bicarb doing?
Acid.
Acid, right? So if all three of them are going the same way, it's a combined acidosis with what?
Normal
hypoxemia.
There you go. Normal
oxemia.
oxemia. You wouldn't say normal hypoxemia, you would say normal oxemia. Good. Now, this is another one I wanted to show you that I didn't show you yesterday, because this is the next thing that can happen. And that's called a lab error. Sometimes the lab can make a mistake. All right, sometimes there can be a mistake in the lab. And this is when neither one of the players are going the same way as pH. That cannot happen. When neither one of the players with CO2 or Bicarb are not going the same way as pH, that cannot happen. That is a lab error. Okay, so for instance, pH of 7.1, a CO2 of 10, and a Bicarb of 40. All right, What is pH doing? Acidosis. Acidosis. All right, but what is CO2 doing? What is CO2 doing at 10?
Acid.
CO2, guys, CO2. CO2 is 35.
Alkalosis.
There you go. So if it's 10, it's alkalosis. So alkaline. What is bicarb at 40?
Normal.
Alkalosis.
Alkalosis. Bicarb is 22 to 26. You got to look at your values. You got to remember those values. So bicarb is 22 to 26. So if it's way up in 40 and it is a base, it's alkaline, alkalosis. So look at this. Which one of them is going the same way as pH?
Neither.
Either one. So this is a lab error. One of these players has to be going the same way as pH. If not, it is a lab error. Okay? Don't be scared to say lab error when you're looking at these or when you're doing your oral or whatever. You say, oh, that's a lab error. That can't happen. It cannot happen. Let's look at another lab error. pH of 7.5. CO2 of 62. And a bicarb of 18. What is pH doing? Alkalosis. What is CO2 doing? Acid. What is bicarb doing?
Acid.
So which one of them is following pH?
Neither of them.
Either one. So this is a lab error. It cannot happen. So if they're all going the same way, it's a combined whatever. If they're all acid, it's combined acidosis. If they're all alkaline, it's combined alkalosis. You don't have to say respiratory, metabolic, none of that. If they're all going the same way, it's just simply combined whatever they are. Okay.
What if the pH is alkalosis, but the PaCO2 and the HCO3 is normal?
So if you have a well, then if that's the case, that would probably be an error too. So you're saying like if we possibly had pH 7.5 and the CO2 was 40, right? And the bicarb was 22. All right. What's pH doing?
Alkalosis.
Okay, alkalosis. All right, now, which one of them is following pH?
Neither.
Neither. So it's a lab error.
Okay.
It doesn't change. One of them has to be going the same way as pH. If neither one of them are going the same way as pH, then it's a lab error. Okay? And remember, these two don't lean. Only one that leans is pH. That pH can lean, but these other are definite. Okay? All right. Want to make sure I went over lab error and combined status. Lab error and combined status are possible. So don't be scared when you look and say, well, damn, that's not respiratory. It's not, what you call it? That they don't. Oh, it's a lab error. Neither one of them are going with pH. So that's a lab error. Okay. All right. Or all of them are going the same way. So that's just a combined whatever. Okay. You might see the word combined. You might see complete, but usually you just see combined. All right.
Also, what happens if your P-little-a-O2 is like at 150 or 110?
And we'll get into that when we get into that part, when that's just overoxemia. That's just overcorrected. Like if I have you on oxygen and your PaO2 is 300, then you're over oxygenated. Okay. Overcorrected. So we're gonna learn that when we deal with corrected and uncorrected or overcorrected oxemia. Okay, we haven't gotten to that part yet. But if you have a PaO2 of 110, right, and everything else is, or you're looking at what will cause that? If tell me this, if the patient was on room air and you notice that their pH, their CO2 was there, I mean, their ABG. So this patient is on room air, right? Their pH was 7.48. Their CO2 was about 30, and their Bicarb was 24, right? And the P(O2) happened to be about 115. What would be the cause of that? What do you think by looking at what you have? What would be the cause of this 115? Why would this be higher than just regular if they own room air? What's the reason for that? No, they're not getting it from anywhere else. They're getting room air. But looking at what
they
you
got a lot of they got a lot of CO. Their CO is down, so I guess they'll be.
So what will be a reason why they're getting more? Why they have a higher P(O2)?
They blowing out too much CO2.
They're
not getting enough.
They're hyperventilating.
Right.
If I'm sucking in more air, then I'm sucking in more what?
CO2.
No.
Oxygen.
Oxygen. Even though it's 21%, I'm putting more in. Okay, I'm sucking in more of it. So my PaO2 can creep up a little bit higher than 100 because I am hyperventilating. If I'm looking at this person is hyperventilating. This is respiratory what? This ABG is respiratory what?
Alkalosis.
Alkalosis. Alkalosis. Can't be acidosis, guys. This is 30.
This is 30.
30 is low. Okay, so it's respiratory alkalosis. So you have somebody who's hyperventilating. It's possible that their P(O2) might be a little higher than normal because he's sucking in more, right? He's sucking it in faster than you are. If you're breathing 12 times a minute and he's breathing 20 times a minute, then he's going to suck in a little bit more than you did. Okay, even though it's the same percentage, he's getting more in faster. All right, so that's the only reason that you would see that, and that's okay. Okay, this still will be a normal oxemia. Just because it's more than, if it's like 110, 115, something like that, it's not over ox. It's just normal. It's okay. He's probably just hyperventilating. Okay. What?
I don't know if that's true, but how do we really know which way it's when looking at the normal values between the P(O2), how it's normal, mild, moderate, and severe? How do we know which way it's leaning?
It doesn't lean.
Or acid or base.
PaO2 doesn't have anything to do with acid base. Remember, I said that over and over again.
Oh, yeah.
Oxygenation and acid base is completely two different trees. Okay, those are two different trees. Okay, this is my acid base status. And this is my oxygenation. Okay, two different trees. So that's why we say respiratory alkalosis with normal oxemia. Okay? Two different things. You can't worry about the PaO2 and how it confirms with the acid base part. They don't go together. Okay? All right. All right, let's go back to the video.
Which is identifying whether it is compensated or
into the
uncompensated. My twin brother Ben will be explaining more about this. So Ben, take it away. Thank you, Don. So we have learned steps 1 and step 2 of reading ABGs. Step number 3.
All right, guys, we're going to take a break now. We just went over the ABG Made Easy video, went over some basics about acid base, and now went into compensation and whether the compensation is either partially or fully. We've gone over that. You can do that like a dead horse, but you have to keep on practicing. All right. It is 2:17. Let's come back at 2:30. At 2:30, we will resume the lecture at carbon dioxide transport. That's what we're getting ready to talk about. How is CO2 transported in the blood? So I'll see you back at 2:30. All right, guys, so we're going to go ahead and move forward. It's now 2:30. And we're going to get into carbon dioxide transport. Carbon dioxide transport. Let me show you the lesson plan. All right, here we go. Here we go. CO2 transport. Carbon dioxide transport is produced, or carbon dioxide is produced from normal metabolism. We know that the burning of glucose along with oxygen is carried in plasma in the red blood cells. Okay, so when we metabolize, what is that? Can y'all see my screen?
Yeah.
Okay. So basic metabolism, like we said, when I'm burning glucose and oxygen together, it makes carbon dioxide. All right. Carbon dioxide is the byproduct of metabolism. Okay. And that carbon dioxide has to be transported so it can get to the lungs so it can be exhaled. Okay. So let's look at the ways that carbon dioxide is transported. First way is in the plasma. Okay, in the plasma, it's dissolved. About 8% of the carbon dioxide that is made from metabolism is dissolved directly into the plasma. 8%. 8% is dissolved in plasma. All right. The second way is CO2 is transported as bicarb. It's transported as bicarb, and this constitutes about 80% of the transportation of CO2 is as bicarb. So best believe you're gonna need to know these percentages and which way. Okay, so 8% of it is dissolved, right? And 80% of it is transported as bicarb. Now, how does that happen? How does that happen? Okay. Here it is. And I'll show you on the, I'll go back to the notes as well so you can write it down. All right, so 8% of the carbon dioxide is dissolved into the plasma. This, inside this box here, is the plasma. This right here, this red part is the red blood cell. Okay, the red blood cell. You got carbon dioxide from the other cells or the tissue level, whatever, coming into the red blood cell. What happens is 80% of it is traveled as bicarbonate. And how does carbon dioxide turn into bicarb? I'm glad you asked. A process called hydrolysis. The process of hydrolysis of carbon dioxide makes carbonic acid. Okay, so you have CO2 plus water equals H2CO3. That is carbonic acid. Okay, the process of hydrolysis. The carbon dioxide comes in and then it mixes with water. That then becomes a new compound called carbonic acid through a process of hydrolysis. All right, so then you have H2CO3. Well, as it continues to travel inside the cell, it loses a hydrogen ion. So it loses a hydrogen ion, and now it goes down to HCO3, which is bicarb. Okay? Bicarb. 80% of it is traveled that way. 80%. And then the last 12% is attached to hemoglobin. Attached to hemoglobin. So that equals 100%. 8% dissolved in the plasma, 12% attached to the hemoglobin, and then 80% as bicarb. Again, how does carbon dioxide turn into bicarb? It turns first, CO2 enters into the cell, it combines with water. Carbon dioxide and water together through hydrolysis now makes a compound called carbonic acid. That carbonic acid then loses a hydrogen ion. So it was H2CO3, but it lost one of the hydrogen ions. So now it's just HCO3. And HCO3 is what?
Bicarb.
Bicarb. Okay. And then the other 12%, like I said, that 12% is attached to the plasma. I'll get a little closer for you than I can. All right, here we go. All right, again, this is the red blood cell here. This is the plasma. This area inside here is the plasma. This is your cell, okay? You have the oxygen-rich blood coming out of the blood will go into the cells, right? And then the carbon dioxide leaves the cell and goes into the, leaves the tissues or tissue cells and goes into the red blood cells, all right? When it does this, it breaks up. Okay, 80% of that carbon dioxide is transported as bicarb through a process known as hydrolysis of CO2. Hydro means water. All you did was take the CO2 plus water. Okay, CO2 plus H2O gives you H2CO3, which is carbonic acid. Okay, that carbonic acid then loses a hydrogen ion. See, 2 hydrogens and 1 carbon and 3 oxygens. Well, it loses a hydrogen ion, so now it's simply HCO3, which is bicarb. All right. 80% of the CO2 that is transported this way as bicarb. Then you have a little 8% will then be dissolved into the plasma. And then 12% of it will attach itself to the hemoglobin protein. That's how it's transported. Those ways. Dissolved in the plasma, attached to the hemoglobin, and carried as bicarb. Now, when this happens, once the bicarb is formed, the bicarb leaves the cell and creates a chemical imbalance. Once this bicarb that was produced by hydrolysis of carbonic acid into carbonic acid, once this bicarb then leaves the cell, see, this is the cell, it leaves the cell and creates a chemical imbalance or electrical imbalance. And so there is a little magic thing that happens when this happens. Cl, which is chloride, does what? It shifts from the plasma into the cell. So when bicarb leaves the cell, creating an electrical imbalance, chloride will then enter into the cell to create balance. That is called the hamburger effect. I don't know why. I don't know if that's his name or whatever, but that's called the hamburger effect, also known as the chloride shift. When chloride enters into the cell to create or restore balance, that's called the hamburger effect or phenomenon, and it's known as the chloride shift. That happens because bicarb leaves the cell, creating an electrical imbalance, and so the chloride will then enter into the cell to restore balance. Now, when I say electrical, why do I say electrical? Because Chloride and bicarb are what? What are they? Chloride and bicarb are what? What are they? They're what are they?
Molecules.
Molecules, but what's particular? What are they?
A base.
Wait a minute. Say it again.
A base.
No. Yeah, it is a base. I'm not looking for acid base right now. I'm talking about chloride, bicarb. Those are two of your what?
Electrons.
Electrolytes. Those are two of your electrolytes, right? We got sodium, you got bicarb, you have potassium, chloride, magnesium, right? Those are all electrolytes. And the electrolytes are for special functions. Who remembers what two electrolytes are needed for your heart to beat? What are the two electrolytes that are needed? They move it in and out of the cell in order to cause systole.
Potassium, one of them.
Potassium and
Sodium.
sodium. Which one is already in the cell? Potassium and sodium on that side, right? That sodium creeps into the cell of a potassium-rich cell and causes a systole or contraction. When that happens, that contraction will push the sodium back out of the cell and restore balance, which is repolarization, right? So when the potassium-rich cardiac cell has sodium to creep in, it causes a depolarization of the cell, which is systole, which is squeeze, right? Contraction. When that contraction happens, it pushes out the sodium back into the interstitial space. And that is repolarization or relaxation of the cardiac cell. Well, in other cells, you have other electrolytes that are working together, which is bicarb and chloride, okay? So when you metabolize and you eat food and you breathe in oxygen, you create that respiratory quotient, right? The unequal exchange of CO2 produced to oxygen used, right? That inexorable change is your metabolism. And so that CO2 has to get back to the lungs to get out, right? So in order for that CO2 that you just made during your metabolism, it has to be transported. And this is how it's transported. 80% of it through a process of hydrolysis makes carbonic acid, which is H2CO3. That carbonic acid then loses a hydrogen ion and turns into bicarb, which is HCO3. All right? And then it comes out of the cell, leaving the cell electrical imbalanced. When that happens, chloride said, okay, I'll take care of it. And chloride will enter into the cell, creating balance or restoring balance. And that movement of chloride is called the chloride shift. It shifts into the cell to create balance because bicarb left. So 80% of it is done this way. 8% simply just dissolves in the plasma, and we'll look at some details on that dissolving. And then 12% attached to the hemoglobin. Those are the three ways that CO2 is transported. You will need to know the three ways that CO2 is transported and what are the percentages. They might say, what is the highest percentage way that CO2 or most CO2 is transported how? Most CO2 is transported how?
The hemoglobin.
No.
Bicarb.
That's bicarb. 80% is transported as bicarb. 12% is attached to the hemoglobin and 8% in the plasma. So Kelsey, don't get confused with CO2 and O2.
I don't know. That's what I did.
That's all right. All right, so this is carbon dioxide going into the cell, red blood cell. 80% of it will combine with water and produce carbonic acid. which then loses a hydrogen ion and becomes bicarb. Okay, that's the most way it happens. That bicarb then exits the cell, creating an electrical imbalance. When that happens, chloride will then shift into the cell and restore the electrical imbalance in a process called chloride shift, or also known as the hamburger effect or hamburger phenomenon. Okay, so if they ask you about the hamburger effect, you have to be able to explain that. What's happening and why does it do it? Okay, if you say, oh, hamburger effect is when chloride enters the cell. Well, they say, well, why? Why does chloride enter the cell? You got to know, because bicarb left and left a electrical imbalance during CO2 transport. Okay? All right. Let's look at the lesson plan for the notes. All right. Why it's important to be here live, because trying to miss a day, this is a lot of information. All right. Go back to the lesson plan. All right, so here it is. Number 2, we said as bicarbonate. Y'all see my screen? Okay. Number 2 is, I don't know what this is now. Okay. As bicarbonate, which is HCO3, CO2 plus water form carbonic acid, which is H2CO3. It disassociates into bicarb and hydrogen ions. That's what it's saying. It loses a hydrogen ion in this equation. Water plus CO2 equal carbonic acid. Okay, which is H and then HCO3. Okay, it will lose that hydrogen ion and become a just bicarb. Okay, once it gets that becomes HCO3, it will lose a hydrogen ion and become just simply bicarb. Right? How much of it is done this way? 80%. 80% of CO2 is transported this way as bicarb. Don't say in bicarb, it's as bicarb. It's kind of like a disguise. Then number 3, attached to plasma proteins like hemoglobin is 12%. 12%. Now, this is kind of what we just said. This is kind of, they keep it in a nutshell for you. In red blood cells, you have dissolved is about 8%, as bicarb is 80%, and then attached to the hemoglobin is about 12%. When we're looking, especially in the red blood cell, dissolved is 8%, as bicarb is 80%. And then they explain what I just told you as bicarb. HCO3 is produced by hydrolysis of CO2. Okay, after we get through all that hydrolysis, it becomes carbonic acid, it loses a hydrogen ion and becomes bicarb in that process, okay? Then the bicarb diffuses out of the cell. It leaves the cell and creates an electrical imbalance. Then chloride, which is Cl, will enter the cell and bring balance back. And that shift is called the hamburger phenomenon. Who can tell me what the normal chloride level is? Those could be on any test.
3.25 to 4, 3.25 to 4.25.
No, I don't think so.
96 to 105.
There you go. 96 to 105 is the normal chloride. So you see why you got to have your electrolytes. So what if you didn't have enough chloride in your diet? right? Then you will always have that electrical imbalance in your cells because you don't have enough chloride to go in to restore balance. So you have to make sure that you are taking in the proper foods in order to get your nutrients, your vitamins, and your electrolytes. They're very important. Just like we said, if you don't have enough potassium, then you can have a problem with your depolarization, right? You don't have the right sodium in and the right amount of potassium. You can have problems with your heart, okay? And then, of course, chloride and all other things. All of them have special properties. So that's why you have to make sure you're getting all your nutrients in because they are very important. The electrolytes are extremely important, okay? So this shift is called the hamburger phenomenon, all right? And then in the red blood cell attached to hemoglobin molecules, 12%. So 80, 8, and 12. 80, 8, and 12. That's what you're going to be tested on. But not only, you know, when I talk about as bicarb, you need to know the process. How does that happen? You need to be able to explain that to me. You need to be able to understand that, not just remember, oh, it's 80% bicarb. You know, you need to be able to apply it, okay? You need to be able to apply it to the cell and to the function of your patient. All right, then we have something called the Haldane Effect. The Haldane Effect is the effect of oxygen on CO2 transport. The effect that oxygen has on the way CO2 is transported. And they're going to talk about at the lung level and at the tissue level. The effect that oxygen plays on carbon dioxide transport is called the Haldane Effect, okay? We talked about the Bohr effect already. We said when CO2 come around, hemoglobin wants to pick it up, right? And that's the Bohr, it's Mr. Bohr, right? CO2 is Mr. Bohr, well, oxygen is Haldane. What happens is at the lungs, the PO2 is increased, which is the oxygen pressure inside the lung. That's what they're not being specific with A or big A and all that. They're saying at the lungs, the pressure of oxygen is increased. And because of that, carbon dioxide is then unloaded off the hemoglobin. All right? All right. And what they're saying is, at the lung level, so Haldane effect. At the lung level, the PO2 is increased. At the lung level, the PO2, the pressure of O2, pressure of oxygen, and the lungs. So I'm gonna draw alveoli. Right? And then of course the blood is the hemoglobin, right? The hemoglobin is in the blood. Okay? So we have our hemoglobin molecule there with the hemoglobin, okay? And this is your alveoli. At the lung level, the oxygen is high. Why is it high at the alveoli? Because you just did what? Why is the pressure of oxygen? You just inhale. The pressure of oxygen at the lungs is high, right? Because you just inhale. So O2 is increased. At the lung level, the PO2 is increased, right? Because you just took in some oxygen. So because the level of oxygen in the lungs is so high, then the hemoglobin will offload the CO2. Because of the pressure in the pressure of oxygen at the lung level is high. So when the hemoglobin sees that, They say, oh, okay, well, let me give you this CO2. Okay, the hemoglobin will give CO2 to the lungs because the lungs already has a high level of oxygen. That's the Haldane effect. We want that to happen, right? We want the CO2 to be offloaded off the hemoglobin. If not, it's going to keep circulating. We'll never blow it off. So it drops it off to the lungs so the lungs can exhale. Okay? That's the lung level. All right, let's look at the tissue level. The Haldane effect. The Haldane effect at the tissue level. At the tissue level, we have the opposite. I'll let you write it. At the tissue levels, the PO2 is decreased. Right? The PO2 is decreased, so CO2 is loaded onto the hemoglobin. Okay? At the tissue level, I guess I'll just write like, this would be like the tissue. All right, this is just the tissue. Not an artist. But at the tissue level, let me take off the share so you can see it better. At the tissue level, the PO2 is low. The PO2 is decreased. And so here's my hemoglobin here. All right. Well, since the PO2 is low at the tissue, what did it say happens? Huh? CO2 is loaded onto the what?
Hemoglobin.
So CO2 is loaded into the hemoglobin. Because at the tissue level, the oxygen is low, right? Because you used it up. You're using it up because you're metabolizing, right? So as you're metabolizing, that oxygen that got to the tissues now has been used. It's been burned. You burned it with the sugars and the chitlins and the chicken, right? All the stuff that you ate is used and burned with the oxygen. So at the tissue level, the oxygen is now gone, right? It's down. And because of that, CO2 said, all right, well, I'll leave. And it goes to the hemoglobin to come back to the lungs so it can be exhaled. That's the Haldane effect. The effect that PO2 or oxygen has on the way CO2 is transported. That is why it's getting transported, because at the tissue level, the PO2 is low. And so the CO2, because the PO2 is low, the CO2 leaves the tissue and goes to the hemoglobin. At the lung level, the PO2 is high, right? And so then it will go where? Off the hemoglobin into the, there you go. It'll jump off of the hemoglobin into the lungs so that the lungs can blow it out. That is the Haldane effect at both levels, the lung level and the tissue level. It's simply the effect that oxygen has on the way CO2 is transported, okay? That's all it is. Haldane effect is the effect that oxygen has on CO2 transport. All right, there it is. At the tissue level, the PO2 is low, right? It's been decreased because of metabolism. You're using it, right? You used it. And so then the CO2 is then loaded onto the hemoglobin so it can return to the lungs to get exhaled. See how much stuff is going on with every beat of your heart? Not only is it just going to the hemoglobin, but it's also being transported as bicarb, and some of it is oozing into the plasma. All this is happening so you can, every breath, right? So you can exhale. Every time you exhale, all this has happened. That CO2 formed with water, became carbonic acid. It lost the hydrogen ion, and it became bicarb. Bicarb left the cell. Chloride entered the cell, bring back balance. At the lung level, The CO2 is then dropped into the lungs. It leaves the hemoglobin, goes to the lungs so you can exhale. And at the tissue level, at the same time, the tissue level, CO2 is low in your tissues. And so the hemoglobin then, or the CO2 is uploaded into the hemoglobin to return to the lungs to do it again. And the engine that pushes the blood all over the body is what? What engine is pumping this blood all over the body?
The heart.
The heart. The heart. So that when the hemoglobin is uploaded, or the CO2 is uploaded to the hemoglobin, it returns to the heart on the right side, right? Goes from the right atrium into the right ventricle to the pulmonary artery and into the lungs. At the lung level, the hemoglobin says, okay, oh, the PO2 is high here, so I'm going to drop the CO2 and pick up the oxygen. Then go back to the heart via the pulmonary veins, to the left atrium, right? To the left ventricle, the aorta, and then to the body. When it gets to the body, it's going to say, oh, the CO2 level is, the PO2 now is low at the tissues because it just used it up during metabolism. And so since that's the case, the PO2 is low at the tissue, so CO2 is uploaded back onto the hemoglobin to return to the right side again to do it all over again. Every beat of your heart, every breath you take, this is happening. Okay? And you have to be able to apply what I just said. You have to be able to understand, okay, well, this is happening, and the heart is moving it, and what side of the heart is respiratory or pulmonary, what side of the heart is systemic. You got to be able to remember those things and apply them to go forward. Okay? All right, now we already learned these things here, terms that relate to CO2. We said hypocapnia, remember, because I said CO2, aka respiratory, aka ventilation, aka acid, aka carbia, aka capnia. Remember all those AKAs, okay? So hypocapnia or hypocarbia is a low CO2 because capnia and carbia are CO2. So hypocapnia, Brittany, will have a CO2 less than what? If somebody's hypocapnic, which means they have a low CO2, that means their CO2 level will be less than what?
35.
35. So that's the normal range for CO2 is 35 to 45, right? Okay. If somebody is hypercapnic, right, which means they have a high CO2 or they're hypercarbic, they will have a CO2 above what?
45.
And then eucapnia means normal CO2, which means that it will be between 35 and 45. So make sure you have those on your AKA. Brittany, you got them on your AKA sheet? That's what I tell you. Make sure y'all have y'all's AKA sheet somewhere separate. Your formulas are separate, your normal values, so you can go back to them. You can refer back to them easily. CO2, aka respiratory, aka acid, aka ventilation, right? Aka carbia, aka capnia. All that means CO2. So hypocarbia means a low CO2 or low acid, low ventilation, right? What about capnia? And okay, no, we already said that. Eucapnia is normal CO2. If I say eucapnia, that means my CO2 is normal. And so I expect to be the range between 35 and 45, okay? All right. We're going to do Henderson-Hasselbeck, and we'll take another break before we go to buffer systems. Henderson-Hasselbeck, you don't have to remember all of this, but this is the formula to find pH. This is how they find pH. pH equals pK plus the log of bicarb over carbonic acid. pH equals pK plus the log of bicarb over carbonic acid. This is how they find the pH of 7.4 being perfect. 3.5 to 4.5 with 7.4 being perfect, right? So pH equals pK plus the log of bicarb over carbonic acid. Now, what is your normal? Let's show you right here. Now, what is your normal bicarb?
22 to 26.
What would be perfect? 22 to 26, what's perfect? Yeah. Bicarb, the range is 22 to 26. So what would be absolute perfect? 24. 24. All right. And then the carbonic acid, they tell you. Hold on.
1.2 milliequivalents per liter.
Yeah, so the normal carbonic acid is about 1.2. Okay. Normal carbonic acid is about 1.2. Okay. So what we do is pK is always what? Can you see it? 6.1? Yeah. Okay. That doesn't change. So pK is 6.1 plus the log of 24 divided by 1.2. So what's 24 divided by 1.2? How much? 2.0. So the log of 2. What's the log of 2?
Right.
Special calculator do log. The log of 2 is what?
1.3.
1.3. So 6.1 plus 1.3 gives you a pH of what? All right, 7.4. That's how they got it. It's on your computer. I mean, it's on your log. You got to be able to do it on your calculator. Log function. Log function. So that's how they found pH, by doing the Henderson-Hasselbalch equation. Henderson-Hasselbalch. He simply said pK plus the log of the bicarb over carbonic acid. And so the reason why they show you this is to show you how it can lean, how you can make pH be acid or make pH be alkaline, depending on your bicarb. All right. So what if you had? Let's look at this. If we just round it off, this was 20 to 1, right? What it was 24 to 1.2, so that's rounded to be 20 to 1. Okay. So let's estimate if I have 30 of bicarb. Let's see what it looks like. pK plus the log of 30 divided by 1. So pK, which is 6.1 plus the log of 30. What is the log of 30? Whoever's got that calculator that can do it. I can't remember. I thought Michael had it. Somebody on here said it.
No, it was on the note-taking guide.
Oh, well, let me look at mine.
1.4, I guess, somewhere in there. 1.47.
Let me look. Is that what you got on your calculator, or you guessed?
No, I'm doing a calculator like off my phone with the log.
So you got what? 1 point what?
1.47-ish.
So 1.5.
Right.
So log of 30 is about 1.5. So if I do 6.1 plus 1.5, what you get?
7.6.
So 7.6, is that alkaline or acid?
Alkaline.
Alkaline.
Alkaline. So you see, if my bicarb is 30, I'm gonna be alkaline because bicarb is a base. Got it? So if my bicarb is up to 30 to 1, if it's 30 to 1, I expect to have a higher pH because bicarb is a base. See, bicarb, if it's 30, it should be 22 to 26, right? But if it's 30, I expect my pH to be elevated, which elevated means alkalosis. All right? So you can do this. You can do this right here. Like if you did an ABG and they didn't give you a pH, if you look at the bicarb, you can kind of guess what the pH might be. Okay, if you just got the bicarb, because what they have is the bicarb will not only be in the ABG, but it will be in the blood chemistry work. When they do a CBC, it also has bicarb because it's got all the electrolytes, and you can use the bicarb number and kind of get an idea of what your pH probably is just by doing that. All right, so now a bicarb of 30 to 1 gonna give me a high pH. Well, what if it's a bicarb of 10 to 1? Let's see what it is with a bicarb of 10. If bicarb is 10, what is that? Acid or alkaline? Huh?
Acid.
Acid. So let's see if that makes a difference with my pH. So, okay, so now we got pK, which is 6.1, plus the log of 10 to 1, which is 10, right? So what's the log of 10?
1.
1?
Yep.
All right. So 6.1 plus 1 is what?
7.
7.1, which is what? Acidosis.
Acidosis.
So I can already know if I get a blood chemistry, and I don't even get an ABG, just get a blood chemistry, and they tell me, well, his bicarb is 10. Well, if I know his bicarb is 10, I already know his pH is going to be around 7.1. Now, you won't have to work this out on the test. You don't have to be able to have log, and I got this test coming up, and I can't do log. Oh, my God. You don't have to do an equation for Henderson-Hasselbalch on the test, okay? You just simply need to know the formula. All right. So that's the Henderson-Hasselbalch. That's just how they found pH. That's how they go about finding pH. All right, because the normal bicarb to carbonic acid ratio is 24, which is perfect bicarb, right? To 1.2 of carbonic acid. It should be about 1.2. That's normal. All right, but you see as it changes, if we do 30 to 1, we have a higher pH. If we do 10 to 1, a lower pH. A low pH, of course, is acid, and a high pH would be alkaline. All right, so let's take a, no, we just took a break, didn't we? Or did we? Did I say we're gonna take a break? All right, let's take a 10-minute break. It's 3:15. Come back at 3:25, and then we will continue on. All right, guys, we're back. I'm gonna share my screen. All right, buffer systems. Buffer systems are simply, the whole purpose of the buffer system is trying to maintain the pH, right? We want to make sure that the pH stays in the middle, all right? And there are 3 main buffer systems, and I'm not talking about compensation systems. Remember, if the kidneys are acting up, if it's a kidney problem, the lungs will try to compensate and help that, right? If it's a lung problem or respiratory problem, then the kidneys will try to fix that problem, okay? Or compensate. But buffer systems is a little different. The buffer system is mainly talking about what we just learned. The Henderson-Hasselbalch, talking about the bicarb over the carbonic acid. Remember we said it should be about 20 to 1, which is really 24 to 1.2. But if you round it, it's about 20 to 1, all right? That is 60% of the buffer systems in your body. The main way the body tries to maintain the pH is through the Henderson-Hasselbalch equation, right? by the bicarb over carbonic acid ratio. That's about 60% of it right there. That's most of it, of the buffer system. Now, we're not talking about transport, okay? I'm talking about buffering, right? Remember, we try to buffer. Whenever the pH gets too acidic, then the bicarb will try to increase to buffer it out, all right? And so the buffer systems are, the first one is the bicarb to carbonic acid, which you just learned in the Henderson-Hasselbalch equation, and how they got to the pHs that we get to, okay? And you saw that if I increase the bicarb, then I'm going to increase my pH. If I decrease my bicarb, I'm going to decrease my pH, okay? The second buffer system, which is about 30% of the buffer system, is hemoglobin. The hemoglobin will do some buffering, right? And the way the hemoglobin does its buffering is through the way we talked about hydrolysis and all that kind of stuff that's going on in the hemoglobin. We talked about the Haldane effect and how CO2 is either uploaded or offloaded in hemoglobin. So all the stuff that the hemoglobin does is about 30% of your overall buffer system. We're talking about the overall buffer system. So 60% is that bicarb carbonic acid ratio. 30% is by what the hemoglobin does throughout the body. And then finally is the blood, just the regular blood, like the phosphates, proteins, sulfates, ammonia group, stuff like that. And what percent would that have to be? 10. 10, because 60 and 30 is 90, 10% is left. Those are your buffer systems. So don't overthink them. The buffer system's main purpose is to maintain the pH. Okay, pH is your hydrogen ions. How many hydrogen ions are in the body? Okay, how many hydrogen ions are in the body? That is what determines our pH. An increase in hydrogen ions will decrease the pH. A decrease in hydrogen ions will increase the pH. Just like you learned in the dissociation curve, right? When it shifts to the left, everything's going down, right? Hydrogen ions go down, temperature goes down, 2,3-DPG goes down, right? CO2 goes down. A shift to the right, everything going up, right? Hydrogen ions go up, temperature goes up, 2,3-DPG goes up, and CO2 goes up, okay? And so what they're talking about is we have to figure out how to maintain the pH. So if we're trying to maintain the pH, we have buffer systems throughout the body. The main one is that Henderson-Hasselbalch, right? That how that works, which is the ratio of the bicarb to carbonic acid, right? We just learned how we get pH from that. The hemoglobin and everything it does makes up about 30% of the total buffer system. And then the blood stuff, like the phosphates and proteins and all that kind of stuff in the blood, is about 10% of the buffering system. That is the buffer systems. And just to see this again, it shows you right here, the bicarb to carbonic acid is about 24 to 1.2 because the normal bicarb is 24, the normal carbonic acid is 1.2. So they rounded it to just say 20 to 1. Okay, when you do that, you do the log of 20, which is 1.3. So 1.3 plus 6.1 gives us a perfect 7.4. All right. Now, if that changes, if the bicarb goes down to 10, then you're looking at acidemia because a bicarb of 10 is acid, right? If the bicarb level is 10, that's acidity. That's acidosis. Or if you increase the bicarb to 30, now you're looking at alkalosis, right? Or alkalemia. Because a bicarb of 30 would be alkaline. Okay? So this right here makes up about 60% of your buffering system. Okay? And the whole purpose of the buffering system is to maintain what? pH. So this does the most of it. This right here, right? And then of course they say hemoglobin, the things that go on in the hemoglobin make up about 30%. And then the small little things in the blood like phosphates, proteins, sulfates, they make up about 10%. All right, then we got into, they want you to go into ABGs, which we've already covered ABGs, but I will show you some normal venous amounts. You don't have to memorize the venous values. What they want you to see, you see the pressure of venous CO2, the pressure of venous oxygen. They just want you to see that if I'm looking for, because look, when I want an ABG, I'm gonna have to stick somebody in the artery, right? You have to stick them directly in their artery to pull that blood. It can't be venous blood, it has to be arterial blood, right? That's gonna give us our ABG values. If you notice, if I just wanna know the pH or the ventilation status, then I can just get a venous gas. I don't have to stick their artery. I can tell the nurse, just give me some venous blood, because look how close the PVO CO2 is and the pH. Regular pH is 7.4 or 3.5 to 4.5 in arterial. But for venous, it's 7.36, right? So that's pretty close. Look at the CO2. A normal CO2 in arterial is 40, which is 35 to 45. Well, the pressure of venous CO2 absolute is about 46. So they're really close. So if I don't want to keep sticking my patient over and over again, if all I care about is the ventilation status, then I can just get a venous gas, okay? Because they're really close. I can see whether he's ventilating or not through a venous gas, okay? But what can I not use the venous gas for? What status?
O2 content?
O2. Respiratory is ventilation. I can do that. But the O2, because venous blood has a very low what? Oxygen. So I can't do that to tell if he's oxygenating. That would be retarded, right? I don't want to look in the venous blood to see if he's oxygenating or not, right? I couldn't do that because look at the PVO2. What the normal PVO2 is, 40. What would this be in arterial? What type of hypoxemia is 40?
Moderate to severe.
Moderate, not severe, just moderate. Severe is anything less than 40. Anything less than 40 is severe, but 40 is considered moderate hypoxemia. So if I'm looking at him through his PVO2, I can't get an oxygenation status from the venous, but I can get a ventilation status. So that's all they want you to see is that the venous values are close when it comes to pH and CO2. Other than that, nothing else is close. I'm in a bicarb, of course, but that's not telling me about my ventilation status. Okay. If I only want to know is am I giving this patient enough volume? Are they ventilating well? Are they getting off enough CO2? And I've been sticking them every hour in the vein, in the artery. That hurts. That is the most painful stick you have is your artery. I don't know if you knew that, but an arterial blood gas is extremely painful, okay? Because the body's saying, hey, you aren't supposed to be in here, right? It's letting you know you ain't supposed to be in this artery. So it's really painful. Just like a heart attack lets you know you're having a heart attack, right? Because it's important. And so if I don't want to keep sticking them, then I can say, well, if all I want to know is his ventilation status, then I can just get the little blood from the nurse. Hey, can you give me a little bit of, give me 1 cc of venous blood and I'll run it, right? And I just want to see what his CO2 is in his venous blood. I can pretty much guarantee, guide whether he's ventilating or not, okay? But if I want to know his oxygenation status for real, I can't get a venous. I have to get arterial. Okay, and if I have to keep sticking them, we do what's called an arterial line. You as a respiratory therapist will start an art line. Okay, you stick the artery, then you'll feed the wire in and pull the guide wire back, tape it down. You have to monitor where it is, set up the actual monitor, and it's gonna have a waveform up on the monitor it gives you an exact blood pressure. Okay. So when you put an art line in somebody, it gives you them an exact blood pressure on the monitor, okay? And then I can pull from the art line instead of sticking them all the time. I can just get a sample from the art line and get my ABG all day long without constantly sticking them. Respiratory starts art lines. Now, some cities you don't, but some states that you do. You're going to be trained to do it, but some states will let you do it, some states won't, okay? Refuse what? You let them know what the possibility is and then chart it. They got the right to refuse, especially if you don't know what you're doing. That's why you need to, it's not, you don't get it every time. You have to feel where the pulse is. And where you feel the pulse, that's where you stick, okay? And it'll flash into you because that's beating, right? So it'll fill up quick and it'll be bright red. It'll be red like this pen. Arterial blood is bright red. But if you're in a vein, it's going to kind of look like this. The blood looks like this coming from the vein because it's deoxygenated, right? Deoxygenated. All right. So that's just the difference between those values. You already know your normal values for your ABG. Okay. Don't forget about the oxygen content, right? The normal oxygen content. I told you that's going to tell you whether we're hypoxic or not, but we're about to get into that in a minute because we're done with ABGs. Now, if you want to go back, I'll scroll through here because they teach you ABGs a little bit harder way. Okay. But if you want to do that, that's fine. I will leave it up there for you. All right. What? What are you talking about? 18 to 20%. Total O2 content, 18 to 20%. See? Okay. All right. So then we talked about compensation, right? Compensating. This is how it compensates. When you have respiratory acidosis, the kidneys will try to fix that. If you have metabolic acidosis, the lungs will try to fix it. If you have respiratory alkalosis, the kidneys will try to fix it. And if you have metabolic alkalosis, the lungs will try to fix it. It's a couple. They're a couple. They go hand in hand. They compensate for each other. Okay? Now, how do they compensate? Here it is. The kidneys, all right? The kidneys are our metabolic system, right? The bicarb. What happens? The kidneys will excrete hydrogen ions, which increase the bicarb, all right, to compensate for an increase in CO2. So if the CO2 is high, the kidneys will excrete more bicarb in order to increase the, if the CO2 is high, then the kidneys will excrete more hydrogen ions in order to make more bicarb, because bicarb is a base, so it's trying to compensate. All right. If the kidneys say, there's a whole lot of CO2 here, let me go back to the lab and make some more bicarb. Okay, I'm gonna throw some more Rolaids at it. Right? The CO2 is high, which is an acid, right? The CO2 is an acid. If it's high, the kidneys will try to compensate that by making more bicarb. All right. And the opposite is true. It will excrete less hydrogen ions to make less, and make more bicarb to compensate for a decrease in CO2. So if the CO2 is low, we're alkaline, right? And so this should be less. All right, it should be less. If there is a respiratory alkalosis, that means the body is alkaline. Well, the kidney's not going to make more bicarb to make us even more alkaline, right? It's going to make less. It's going to excrete less hydrogen ions to make less bicarb, right? Take some of the Rolaids off because we already respiratory alkalosis. We don't want to be even more alkaline, right? Let's take some of the Rolaids off of it. Let's make less bicarb because bicarb is a base. CO2 is acid. Now, one thing that's important about the kidneys, look how long it takes for the compensation to work. How long does it take it to work? 3 days. So it takes about 3 days for the kidneys to be able to compensate for that respiratory issue that you're having. If you're having a respiratory issue, it's going to take the kidneys about 3 days to fix it on their own. Okay, now we can fix it as respiratory therapists, but the kidneys take on their own, going to take about 3 days to try to fix it. So, and they're saying this a whole lot of different ways, guys. It's all the same thing. If you have a lot of acid in the lungs, then the kidneys will try to make more bicarb. Simple as that. Okay, to try to buffer it out. If you have a really low CO2 and you're becoming alkaline, well, then the kidneys will make less bicarb so you don't overdo it. Okay, to try to buffer it back out. That's all it's saying. Then what about the lungs? The lungs work themselves as well. We can decrease the carbon dioxide to compensate for a decreased bicarb. If the bicarb is low, that's what? Low bicarb is what?
Acid.
Acidosis. So the lungs will decrease the CO2 by doing what? How can our lungs decrease the CO2? Breathing what?
Oxygen.
No, y'all don't say oxygen. We're not talking, they're two different things. How can the lungs decrease the CO2 if they need to decrease it?
Breathing faster?
By hypoventilating?
Hyperventilating. Hyper, right? So if the body sees that we are in a acidosis, metabolic acidosis, see, a decreased bicarb. Okay, if the bicarb is low, that's acidosis. So if the lungs see, we're in an acidosis, I'm gonna fix that. The lungs fix it by decreasing the CO2. And how do they decrease the CO2? They breathe faster. Because we decrease CO2, we blow off CO2 regular, but if I need to blow off some more, I need to breathe a little faster to get it off. I don't need to breathe in oxygen. That's not going to fix it. I need to blow off the CO2 because CO2 is an acid. All right. Oxygenation and blood gas status is two different things. Two different things. Okay. We're talking about compensation for the acid-base status. We ain't talking about oxygen at all. When we're talking about buffering systems and we're talking about compensation, it is simply CO2 and bicarb. No oxygen, got nothing to do with this. Okay, nothing to do with this at all. All right, so we said when we talk about compensation, we said the kidneys can compensate by either increasing or decreasing the bicarb. That's how they work. The kidneys will either increase or decrease the bicarb to fix the problem. The lungs work by either increasing or decreasing the CO2. Okay, we either increase the CO2 or decrease the CO2 to fix the problem. All right. Now, number 2 says the lungs can increase CO2 to compensate for an increase in bicarb. If the bicarb is high, what is that?
Acid.
Acid. No.
Alkaline, my bad.
There you go. If the bicarb, so look at this, guys. If the HCO3 is high, that is what?
Alkaline.
Alkaline. Alkalosis. All right, and this is the kidneys. I can't draw, but the kidneys. All right. The bicarb is high, that's alkalosis. Now, how can the lungs fix alkalosis? the lungs will try to fix an alkalosis by making more acid, right? So how would the lungs make more acid or retain acid? Huh?
Hyperventilate.
Say it again.
Hyperventilating.
If I hyperventilate, I'm gonna make more alkalosis.
Hypo.
I gotta slow down, right? If the lungs slow down, they will increase the CO2. All right, so the lungs, put it like this. The lungs increase CO2 by hypoventilation. Got it? The lungs can increase CO2 by hypoventilation. The lungs decrease CO2 by what? Hyperventilation. All right, so this is the lung. All right, this is how the lungs compensate. So write that down. The lungs compensate by either increasing the CO2 by hypoventilating or decreasing the CO2 by hyperventilating, because CO2 is an acid. So we can either increase the acid or we can decrease the acid, okay? We can increase the acid by hypoventilating. If I hypoventilate, I'm going to increase my acid or my CO2. CO2, aka acid. If I want to decrease the acid, then I need to hyperventilate. That's it. Just don't make it harder than it is. All right, so let's look at the kidney. When I say the kidneys, so kidney can increase the bicarb, right? Or it will decrease the bicarb. That's how the kidney compensates. It's either going to increase the bicarb or drop the bicarb. So if we are, this is a question. If we are in a, put it like this, a respiratory acidosis. Say we are in a respiratory acidosis. Which one of these would the kidneys do? Which one of these right here would the kidneys do in response to respiratory acidosis?
Hypoventilation.
No. I'm talking about kidneys right now, guys. If we're in a respiratory acidosis, what
they would make
It's going to create
less bicarb.
If it creates less bicarb, that's
going to create more. It's a base.
Yeah, so it has to increase the bicarb. So in response, we're talking about compensation or response, okay? If we are in a respiratory acidosis, the kidneys will respond by increasing the bicarb to get rid of the acidosis, okay? What if we are in a respiratory alkalosis? All right, we are in a respiratory alkalosis. How will the kidneys respond to fix this?
Decrease bicarb.
What did you say? Who said that?
Stephanie, decrease the bicarb.
Decrease the bicarb. No, not decrease. Or is it? Wait a minute. If they're, yeah, you're right. If we're in an alkalosis, we need to decrease the bicarb to make more acid. Okay? So good. If we're in a respiratory alkalosis, the kidneys will work by decreasing the bicarb. Because if we decrease the bicarb, we make ourselves become more acid to even that out some. All right? Good job. What if we are in a metabolic acidosis? If we are in a metabolic acid state, what will the lungs do to fix that? I'm talking about lungs, we're talking about compensating. If we are in a metabolic acidosis, what will the lungs do to fix it?
Hyperventilate.
Thank you. The lungs will hyperventilate to decrease the CO2, which is acid. So that's all they know to do. Well, if you acid, then I need to release some acid to give us back even. Okay, now you're getting it? What if we are in a metabolic alkalosis? If we are in it, so listen before you say anything. If we are in a metabolic alkalosis, what will the lungs do to fix that? Hypoventilate, because if we hypoventilate, we're going to increase the CO2, which is an increase in acid.
Mm-hmm.
All right. So this is the compensation that they're talking about. The kidneys will compensate for the lungs, and the lungs will compensate for the kidneys. Okay? If the lungs acting up, the kidneys try to fix it. If the lungs are acting up, if the kidneys are acting up, then the lungs will try to fix it. Okay? Good. And just remember that the kidneys take about 3 days to do their fixing, but the lungs can fix it immediately. All right? All right. So make sure you go back and look at that, what we did as you study, because it's a lot of up and downs, left and rights. And if you get confused, and if you're just trying to memorize, you need to learn the material so you don't have to rely on memory. Oh yeah, that go up, and if that go up, this go down. That'll never get you where you need to go. You need to remember. So if you know why and what's going on, then you can process of elimination these answers. Okay. You need to know that the kidneys will help out a lung issue by either increasing the bicarb or decreasing the bicarb. Okay. The lungs will help the kidneys out by either increasing the CO2 or decreasing the CO2. Okay. That's what you need to know. All right, we're almost done. We can also compensate pharmacologically. If the kidneys and the lungs are not doing it enough, we can do it with medicine. We can do it with medicine. And what medicine will we use? Well, we can give sodium bicarb to increase the pH. I can give you some medicine, some liquid sodium bicarb. Okay? Sodium bicarb is a bag. You can get a nice bolus of sodium bicarb, or it can be an amp of bicarb. But if your pH is really, really low, we're going to give you an amp of bicarb. We're going to shoot you with some bicarb, because evidently the kidneys are not producing the bicarb like they should, so we got to give it. People who are in kidney failure will have this problem. Okay? Because if your kidneys ain't working, they're not going to be able to do what they're supposed to do. Not only are they not letting you urinate like you're supposed to, right, and get rid of those impurities and all that, you might be on dialysis. People who are on dialysis, their kidneys are not functioning well enough to keep the impurities out of the blood. The kidneys are the filter of the blood. All of the blood goes through the kidneys, and the kidneys will filter that, all of the mess out, right? And then you pee it out, okay? But if your kidneys are not functioning, then you have to go on dialysis. Otherwise, your numbers of your kidney failure, your numbers, your BUN, all that kind of stuff, your blood urea nitrogen, the nitrogen in your blood and ammonia and stuff gonna start building up because you can't pee it off, right? And then not only that, you're gonna start retaining water, and water start leaking into your lungs. Then you can't breathe, right? It's just all kind of stuff. Dialysis, yeah, because our kidneys are not functioning. Yeah, they put a line in you and they will hook you to a dialysis machine. It will pull all your blood out, filter it, and put it back. That's what the kidneys are doing. But the kidneys, if the kidneys don't do it, we have to do it for you in dialysis. Okay, and so they'll be having these issues. And so, so for somebody whose pH is really, really low, that means they're very, very acidic. It's acidosis. Low pH is acidosis. So we can give them some liquid bicarb to raise that pH back up some. Okay, and then the opposite is true with ammonium chloride. If somebody pH is really, really high, somebody walking around with an 8 pH, and we can't get it down, the lungs are not working to get it down, then we can give them some ammonium chloride to drop that pH. Okay, you want the pH to be in normal range, otherwise medicines don't metabolize. Okay, it's hard to metabolize if your pH is jacked up. So if your pH is an 8 or a 6, and I give you medicine, it may go in and come right back out. It never gets processed because your pH is not right. pH being off can cause yeast infections in women if your pH is not right. Okay. All right. So this is the interpretation, guys. I've already taught you. This is the ABGs talking about uncompensated, partially compensated, compensated, yes, no, and all of that. That was the hard way. I don't know nobody that likes this way, but it's here. If you want to pause it and go back and look at it, you can. But I've already taught you.
What does the BE stand for?
BE is, I told you, that was base excess. You really, rarely see that. Anything you got to do about it. BE is base excess. That's either the person has got a little bit of dehydration or overhydrated. That's all that is. It's usually plus or minus 2, I think. If somebody has a base excess of 10, that may mean that they have too much fluid on them. Okay, but that's nothing that you'll have to deal with as a respiratory. All right, so that section there was about interpreting ABGs, and that's what we've already done. I gave you the 3-step method to first see what pH is doing. 2 is to see who's causing the problem. That's number 2, right? Player 2. And then look at the third player. Is the third player out of normal range or not? And that determines your compensation. All right? And that's it. That's it. Now, hypoxemia. Hypoxemia, which is a lack of oxygen in the blood. This is the second part of your ABG. Remember, you got acid-base status, and then you have an oxygenation status. They are not the same. Every time you say this the same, you need to tap your hand. It's not the same. Okay? It's not the same. Now, that number is determined by my P(a)O2. So either my P(a)O2, which is the partial pressure of arterial oxygen in my blood, or I can look at the O2 content amount. They can tell me whether the patient is hypoxemic or not. And you already know that P(a)O2 is 80 to 100 millimeters of mercury. So for instance, if I have a P(a)O2 of 35, what is that? What kind of hypoxemia is that? Severe. What if it's 52? Moderate. What if it's 80? Normal. What if it's 75? Mild. What if it's 40? Moderate. Less than 40 is severe. Okay? And they will try to trick you on that. So that's how we assess hypoxemia with the ABG, right? So we can say, okay, for instance, this patient has a normal blood gas with normal oxemia, or they have respiratory acidosis with normal oxemia, or they can have metabolic acidosis with mild hypoxemia, right? Those are two different parts. You have to be able to say them both. The acid-base status, as I told you yesterday, or it might have been today, the acid-base status is the pH, CO2, and the bicarb. That's the acid-base part. The P(a)O2 is the oxygenation. All right? Two separate trees. All right? And we did a few of those yesterday. Is there any question on the hypoxemia as far as the P(a)O2 is concerned? Does everybody remember that you have to say them both? So for instance, if I have a ABG that says ABG, I want to hear you say it correctly. pH of 7.4, CO2 of 40, bicarb of 24, and a P(a)O2 of 36. What is this ABG? The whole thing. You say it out loud. You don't have to put it in the chat. Just tell me what it is.
Is it a normal ABG with severe hypoxemia?
Excellent. Normal ABG with severe hypoxemia. If you look at the pH, 7.4 is normal. The CO2 of 40 is normal. Bicarb of 24 is normal. A PaO2 of 36 is severe hypoxemia. So this is a normal blood gas with severe hypoxemia.
So why is it hypoxemia and not hypoxia?
Because we're talking about arterial blood. Hypoxemia is low oxygen in arterial blood. P(a)O2 is the pressure of arterial oxygen.
Okay, so it's just because we have the little a.
Yes.
Okay.
All right. What about this one? 7.35, CO2 of 52, bicarb of 30, and a PaO2 of 76.
Is it fully compensated metabolic alkalosis with mild hypoxemia?
Oh.
No, it's fully compensated respiratory acidosis with mild hypoxemia.
That's it. pH is 7.35, which is normal, but leaning acidosis. Who's causing the problem? CO2 is acid. Bicarb is alkaline, so CO2 is causing the problem, right? So he's the second player. Bicarb would have to be the third player. So since CO2 is causing the problem, we are in a respiratory acidosis. So then we look at our third player. Is he in normal range? No. So we have compensated respiratory acidosis. Now, what kind of compensation? Well, is bicarb's compensation enough to pull pH back into normal range? Yes, because you said it was normal. So it is fully compensated respiratory acidosis with, let's look at the PaO2. P-little-a-O2 is 76. That is mild hypoxemia. That is it. That's as hard as the ABGs get. All about being able to continue to practice them and to be able to say it. That's it. Excellent. But you got to study it. You don't spend the time on it, it's going to be gone bye-bye. All right, so that is how we do ABGs. You see, it's two different things. There's an acid-base status with an oxygenation status. ABG status with oxygenation status, okay? They're not the same. You don't say, well, if he's not ventilating, what should I do? Give him oxygen? No. Oxygen got nothing to do with ventilation. They're two different things, okay? All right. Now, so that is how we determine whether our oxygenation status as far as hypoxemia is concerned with the P-little-a-O2. Hypoxemia is simply low oxygen in the blood. Hypoxia is low oxygen at the tissue. There is no cutoff number that changes from hypoxemia to hypoxia. None of that. If you're talking about the blood and the oxygen, it's hypoxemia. Okay? Now, the second way to know about hypoxemia or not is the total O2 content. And you guys already learned how to do total O2 content, right? Everybody, we did that in the homework this morning. Total O2 content was the dissolved plus combined with hemoglobin, right? And these are the numbers. If you have 15 to 17 is mild hypoxemia, 12 to 14 is moderate, and anything less than 12 volumes percent is severe. Yes. Because you may have a test question that gives you, say, Mr. Smith had a total O2 content of 13. What is his oxygenation status? You got to know that that is moderate hypoxemia. (18 to 20 is normal. Don't worry about this over 60 years old. I think they've been changing this a little bit. This is a little old, but they're just saying that if you're over 60 years old, you can subtract 1 millimeter of mercury for every year over 60 for your PaO2. So, if they're 75 years old and you can knock off 15 and still be normal, right? They can knock off 15 instead of 80. It could be 65 or something like that. We ain't worried about all that. Just go by this right here and this right here. This is how it's going to determine whether you're a hypoxemia or not. That 60-year-old stuff, they don't really do that much anymore. You won't even see that. Probably maybe later you can worry about that on down the road. But right now, to determine whether your patient is hypoxemic or not, you can look at their P-little-a-O2 status or their total O2 content status. And what's the last way to know if their oxygen is low? Huh? No. The hemoglobin is part of the O2.
ABGs.
Huh?
ABGs.
Yeah, this is the ABG. The P-little-a-O2 comes from the ABG. I'm talking about what other way can I look and find out whether my patient is suffering from low oxygen?
By the way that they're breathing, if they're using the accessory. Muscles.
That's possible, but that's not what I'm looking for. What's another thing I can look at? Something.
The O2 content? The total O2 content?
That's right here. I already said that. Listen, y'all. This way and this way, yes. Okay. If you look at the P-little-a-O2 in the ABG, that can tell me whether they're hypoxic or not. Or I can look at the total O2 content and find
The
out.
SAT.
Thank you. It's saturation. His little finger probe that you got on his finger. If it's 80, he's hypoxic. Okay. It's saturation. Either the one, the little probe you have on their finger, or the one on the wall, you know, the monitor, the little blue one that's on the monitor. That's his oxygen saturation. So I can look at all three.
Okay. Okay. They already shampooed the first time though. Okay. I'm gonna get it. Okay.
All right. And this is just showing you how to calculate total O2 content, which you already know that. That's the formula. All right, the last thing for this unit is the control of ventilation. We're just going to talk about these peripheral chemoreceptors and central chemoreceptors. This is all that's left. This right here and this right here. That's all that's left. All right. The control of ventilation and what makes us start breathing more or whatever, you have what's called chemoreceptors. Chemoreceptors. You got central chemoreceptors and we have peripheral chemoreceptors. Central chemoreceptors and peripheral chemoreceptors. The central chemoreceptors are influenced by the contents of the cerebral spinal fluid. Carbon dioxide diffuses freely into the cerebral spinal fluid. Okay? When the body senses a high level of CO2 in the cerebral spinal fluid, it tells you, hey, breathe. Central CO2. Central CO2. Okay? The central chemoreceptors respond to CO2 in the cerebral spinal fluid. Central CO2. Central CO2. And all that's saying is, in your cerebral spinal fluid, guys, in your cerebral spinal fluid, carbon dioxide goes in and out of the cerebral spinal fluid easy, okay? Internet acting up. But it goes in and out of it very easy. When the body recognizes increased levels of CO2 in the cerebral spinal fluid, they say, hey, breathe. That's what makes you ventilate. Okay? Because we don't want that to build up, right? We want the CO2 to come off. So once it starts building up, the body says, hey, you need to breathe. Breathe. Okay? The central chemoreceptors respond to CO2. Central CO2. Write that down. Central CO2. So if I say which one of the chemoreceptors responds to CO2, oh, that's the central chemoreceptor. Central CO2. They respond to elevated levels of carbon dioxide in the cerebral spinal fluid. CSF fluid. That's cerebral spinal fluid. Once that level, and there's no level of what it is, but once that level goes up, the body says, hey, the inspiratory center says you need to breathe. Okay, that's how they respond. But you're going to learn later that there is a certain patient that does not respond to the central chemoreceptors anymore because they have smoked their little chemoreceptors out and smoked them all up. Who would that be?
COPD patients.
COPD patients. They don't respond to the central chemoreceptor because guess what? Their CO2 level is always what? High. See, me and you, our CO2 is not always high. So when it increases, the central chemoreceptor say, hey, this ain't right. You need to breathe, right? But if I'm a COPD, I don't smoke that out. So now I'm always high. So they don't know if it's high or not. So they don't even work no more for a COPD patient. Okay? But we'll learn about that later. Okay? But you need to know that our regulation of ventilation, okay, is by either the central chemoreceptors or the peripheral chemoreceptors. We just learned that the central chemoreceptors respond to CO2. The CO2 that builds up in the cerebral spinal fluid. When it gets to a certain level, and I don't know the level, but when it gets to a certain level, it says, hey, you need to breathe. Okay? And that's that on that with the central chemoreceptor. Now, the next one is called the peripheral chemoreceptor. And it works well. I'm going to go down to peripheral and then I'll go back to those. Peripheral chemoreceptors respond to PO2. Peripheral PO2. Peripheral PO2. Peripheral PO2. They respond to a low PaO2 or PO2. They respond to a low PO2. Now, a low PO2 is what? What is this right here? Hypoxemia. If your PO2 is low, you're hypoxic. The peripheral chemoreceptors respond to a low oxygen, which is PO2. So when your PaO2 gets low, the body say, hey, you need to breathe. Simple as that. So the central chemoreceptors respond to CO2, and the peripheral chemoreceptors respond to what? Low oxygen, which is PO2. A low PO2, which is hypoxemia. Now, there are two types of peripherals. There's only one type of central, but there are two types of peripheral chemoreceptors. But what did I say peripherals respond to? Everybody say it.
PO2.
Thank you. A low PO2. And a low PO2 is hypoxia or hypoxemia, right? Hypoxemia is a low PaO2. That is where the peripherals kick in at. So when the peripheral chemoreceptors sense a low oxygen amount or hypoxemia, they say, hey, you need to breathe. But not only do they do that, they also knock on the heart and say, you need to beat a little harder. Okay, so let's see which one does what. There are two types of peripheral chemoreceptors, the carotid bodies and the aortic bodies. The carotid bodies respond to hypoxemia, which is low PO2, right? Let me write it down, PO2, right? Put it in parentheses, make sure you understand. Okay? Carotid body, there's two types of peripheral chemoreceptors. Okay? You have the carotid bodies and the aortic bodies. The carotid bodies respond to hypoxemia, which is low PO2, by increasing the ventilation and they are located in the bifurcations of the common carotid arteries. So your carotid arteries, the common carotid arteries are the carotids. You know where your carotid artery is? Well, there are little bifurcations in there, and they're just located. It's like a little booger. The peripheral chemoreceptor is like a little green booger that's sitting right there on the carotid artery, and it's monitoring. Its whole job is to monitor the amount of oxygen that's in there. That's his whole job. And when that oxygen get low, he said, hey, you need to breathe. That's the job of the carotid body, peripheral chemoreceptor. Now, the next one is the aortic bodies. The aortic bodies also respond to hypoxemia, which is a low P. Okay. They also respond to hypoxemia, which is a low PO2, right? Let me make the color. I want to make sure you guys don't mess this up. Okay. Peripheral PO2. Peripheral, I'm gonna make peripheral be purple. Oh, that even rhymes. Peripheral, purple, PO2. Okay, so don't mess it up. Peripheral respond to PO2. Okay, and then the central central chemoreceptors respond to CO2. Okay, central CO2. So central respond to CO2, peripherals respond to PO2. Okay. Now, the two types of the peripherals were the carotid bodies. We said they respond to a low PO2, which is hypoxemia. And they tell your body, hey, you need to breathe. Once they sense they're low, they say, hey, you need to breathe. Okay. They are located in the bifurcations. That's where they bifurcate, right? The carotid arteries go up and they kind of bifurcate to go into the brain. In those little bifurcations, there's a little booger-like structure that all his job is to sit there and monitor the amount of oxygen going to the brain. Okay? When that oxygen is low, he said, hey, you need to breathe, because if you ain't breathing, you're not pulling in any outside oxygen, right? So you need to breathe. Okay? Now, the next one is the aortic bodies. The aortic bodies, they respond to a hypoxemia, which is low PO2, right? And how do they respond? They affect the heart more than ventilation. So not only do they tell you to breathe, but they also tell the heart to beat faster or harder. Okay? And they are located in the aortic arch. And I'm going to show you where that is right here. The aortic bodies are located right, it's a booger-like structure sitting right on this aortic arch. See, this is the aorta. This is called the aortic arch. It's a little booger-like structure that sits right there on your aorta that monitors the amount of oxygen. So this one, so let me answer this critical thinking, which shouldn't be too hard. If the aortic body is here, then it is monitoring the amount of oxygen going where?
To the body.
To the body. And if the the carotid bodies are up here in the carotid arteries, they're monitoring the blood going where?
The brain.
To the brain. Okay? That's why it's two of them. Because the brain got to have its own supply, and it wants to make sure that the brain has its oxygen. Okay? And that's the operation headquarters of the body is the brain. Okay? So that's why it's two of them. And that's simple, guys. That's it. The carotid bodies or the peripheral chemoreceptors respond to PO2, a low PO2, which is hypoxemia. The carotid bodies respond to the low PO2 going to the brain, telling you, hey, you need to breathe more. Okay? And the aortic bodies are located on the aortic arch that looks at the blood amount going to the body. And if it's low, not only will it tell you to breathe a little faster, but it also will tell the heart to beat harder or faster. Okay? All right. Now, that is the end of RT210E. Oh, yeah, let me go back up here. I'm sorry. Where was I at? Yeah, okay. Yeah, my bad. Okay, so under this, and I like to do the central and then go ahead and knock out the peripheral, so you know the difference between the two. But what they're talking about is the areas of the, didn't we talk about this already? I believe we talked about this. I could have swore we talked about this when I talked about the ponds. The pond, no, I'm talking about when I showed you the PowerPoint of the ponds and all of that. Remember I said you have a, yeah, but we'll go over it again. The apneustic or the pontine center, remember, that's the one that allows for deep inspiration. I said, what is an example of a deep inspiration? A sigh or a yawn. Right, remember we talked about that. And then I said, if you start to breathe too much, your lungs start to stretch. And those stretch receptors are called what? Remember this?
Herringberg?
Yeah, the Herringberg reflex. When the lungs start to stretch to a certain amount, they say, hey, that's enough. You need to stop, right? You remember talking about that? Yeah. Okay. That's all that little part is. But the areas of the medullary center, right? We talked about the medulla, right? And we said the apneustic or the pontine center is located in the medulla area, and they allow for deep inspiration, controlled by the pneumotactic center. Remember, they are the ones that are the checks and balances. The pneumotactic center it limits the inspiration, right? You can inspire, but you can't inspire all day. You're gonna stop when I tell you to stop, right? The pneumotactic center will stop the inspiration when it becomes too much. Well, how will it know if it's too much? By the Herringberg reflex. You stretching your lungs. Hey, that's enough. Okay, that's enough. The most important part of this little section is those two chemoreceptors, central chemoreceptor and your peripheral chemoreceptor. All right, now let's put it together. Let me pull this up. I think we did that one already. We're going to work on this one together. I'm going to share you. These are some practice NBRC questions here, but we still got some time, guys. It's just y'all are not 100% ready, that's for sure, on this part, on this lesson. All right? Acid-base chemistry, because the test is Monday. Acid-base chemistry. These are example. Oh, and there's one more thing. I'm glad I said that, because there's one more thing I need to cover. I'm gonna cover it on, you have to make this note yourself. It's just a real quick thing, but you'll make this note on your own notes, okay? All of the ABGs we've been doing, the patients have been on what? How much oxygen?
21%.
Okay. Well, what is the oxygenation status called if they own oxygen and it still ain't right? Okay? This is how you look at it. When any FiO2 other than 21%, which is room air, you answer the hypoxemia question in this. It's either All right. If you're on anything other than FiO2 or 21%, if I got them on some oxygen, that means I'm trying to correct hypoxemia. If I put you on oxygen, it's because you were hypoxemic at some point, right? If you were hypoxemic at some point, I place you on some oxygen, okay? So then after I put you on oxygen and I get another ABG, then I need to answer the question like this. Either I corrected the problem, it's not corrected, or I overcorrected it, okay? So say I get an ABG and you on 50% oxygen, okay? Patient on 50% oxygen and I get an ABG. If their PaO2 is now 80 to 100, then I corrected it. It's corrected hypoxemia, all right? If I get on 50% oxygen and I get an ABG and it's anything less than 80, it's not been what? Corrected. I haven't corrected it yet. I'm gonna have to bump it up some more, get another ABG, okay? If I have them on 50% oxygen and the PaO2 is like 150, 200, then I have been overcorrected. I need to come down on the oxygen, okay? Because oxygen is a drug and it will kill you. Too much of it, okay? So when I'm answering that with hypoxemia or with whatever, if they're on FiO2 other than 21, you have to answer with corrected, uncorrected, or overcorrected hypoxemia. That's all it is, okay? So for instance, knowing this, I'm gonna put up some PaO2. So let's just say this. I'm gonna sit down so it's kind of low. All right, so knowing this, let's just say Mr. Smith is on 45% FiO2, okay? And his ABG shows me a P(a)O2 of 63 millimeters of mercury. What is that? PaO2 will be what? What kind of hypoxemia? Uncorrected. Because I'm trying to correct it with the oxygen, okay? But I look and I see it's not been corrected yet, right? Like you whip your child and he still keep doing what he's doing. You need to tighten up a little bit more, right? It's not been corrected. That problem has not been corrected. It's uncorrected behavior, all right? But if you pop your child or put him in timeout or whatever y'all do today, and you come back and he's doing what he's supposed to do, then you've corrected it. It's been corrected, all right? So what about if he's on 45% oxygen and his PaO2 is 250?
Overcorrected.
I've overcorrected that, okay? I've overcorrected. And if I have them on, 45, whatever, anything over 21, if I have them on oxygen and his PaO2 happens to be 90,
You corrected it.
corrected hypoxemia. I corrected it. Because if I'm on oxygen, I'm trying to correct this problem. I wouldn't put him on oxygen if he wasn't hypoxic, right? If he was never hypoxic, I would have never put him on oxygen. But because I put him on any FiO2 other than 21% means I'm trying to correct a problem. And the problem is hypoxemia. Okay? I looked at his SAT, it was low, or I got an ABG and his PaO2 was mild, moderate, or severe hypoxemia. Then I gave him some oxygen. I wait about 30 minutes, I stick him again and see what my results are. If our results are now 90, then hey, I corrected it. I put them on 2 liters or whatever I put them on. That has corrected the problem. Okay? That's important. All right. Let's look at this worksheet. NBRC questions. These questions are what some sample acid-base chemistry questions that were on the board exam at some point. Okay, when you took your big exam for the NBRC. So look at number 1 and work out number 1. It says, interpret the following blood gas drawn on 21%. So this patient is on room air. So you don't need to do the corrected and all of that. For him, he's on room air. Okay? Torr is millimeters of mercury. Remember, I told you torr, millimeters of mercury are the same thing. Learned that in 210A. Torr and millimeters of mercury are the same thing. They just like milliliters and cc's, the exact same thing. Torr and millimeters of mercury are the exact same thing. So interpret the following blood gas drawn on a patient breathing 21% O2. He has a P-little-a-O2 of 117. He has a SaO2, which is a SAT of 98%. His pH is 7.57, CO2 of 20, bicarb of 24, and a base excess of +1. What is the answer? And that's Sydney. This is that multiples you don't like. But you can rule things out. Don't forget, if you find one you know ain't right, then you can get rid of it. Now, don't forget, just because your PaO2 is a little more than 100 on room air does not mean it's a problem, okay? It just means that they're probably hyperventilating. You have to look at the rest of your values and see, is he hyperventilating? So I want you to figure out number 1, everybody, and then tell me in the chat what your answer is. So you're going to figure out your ABG, acid-base status, and then find the oxygenation status, and then see which one of these choices would be correct. Put it in the chat directly to me when you do it. These are the kind of test questions that's on the test. All right, so let me see what that answer is. All right, so this is what I would do if I were you. I'm looking at my pH. That pH is what state are we in? Alkalosis, right? So anything that says acidosis, I can get rid of it, right? All right, so choice 4, I can get rid of because I know we're not in no kind of acidosis. So any of these that has 4 in it, I can get rid of. So that gets rid of B and that gets rid of D. Only choice I got now is either A or C. Okay? So now, what's wrong, Shadara? Huh? You did what? Oh, okay. All right. Well, let's look at the pH. It is alkalosis, right? All right. You said it's alkalosis. Let's see who's causing the problem. Well, what's CO2 doing? It's doing what? CO2 is what?
Alkaline.
Alkalosis. Okay. Tor is millimeters of mercury, same thing. So it is alkalosis there. What is bicarb? Normal.
Bicarb is normal.
So who's causing the problem?
CO2.
CO2. So all right, now is bicarb trying to compensate?
No.
No, because it's normal. It ain't doing nothing. So it's uncompensated respiratory alkalosis. All right, so uncompensated respiratory alkalosis. We know 3 is in the answer. Okay. Now, what about the oxygenation status?
Well, you said that was fine because they could just be hyperventilating.
Yeah, it's fine. It's normal. It's fine because he is hyperventilating, right? Because look, his CO2 is 20, so he's hyperventilating. So that is normal. So normal oxygenation. So 1 and 3 for sure. And we only had 2 choices to pick from, so the answer is C. 1 and 3. Look at number 2. This person is interpret the blood gas on a person breathing 60%. He's on oxygen. He's on 60% oxygen. All right. He has a PaO2 of 72, SAT of 94, pH of 7.18, and a CO2 of 50, and a bicarb of 18. The basic says a negative 10. Work on that one. All right, guys. So we had some practice ABGs. I'm gonna share my screen for the ones that I just showed, because I wasn't recording that last little bit. We did 1 together, and then number 2. Okay, number 3, and number 4. For those of you who are watching later and didn't come to class, you can work these out, try to figure them out, and then you can ask me on Monday if you have a problem with them or which one was right. Okay. All right. Other than that, I will be putting y'all's homework in now. It's going to be a couple of worksheets. It might even be a workbook page or 2 to help you practice over the weekend. Do not look at this over the weekend, because it will leave you. On Monday, I will go over a little bit. Not like I'm going to teach it again Monday before your test. I'll go over it when you get here. The alpha group get here at 1. I will review from 1 to 2. You can take your test and go home. Alpha Omega group come in at 4. I will review from 4 to 5. You take your test and go home. All right, but it's going to take you really putting it in, doing the homework, so you can bring them to me on Monday. Say, can you do number this? Can you do number 2? Explain this one. You know what I'm saying? Try to help you with this, because ABGs is the major part of respiratory. You got to know it. Okay, you got to know it. And not only just the ABGs, but the CO2 transport, oxygen transport. That's why you did the other homework, which did all of those samples. Okay, very important you stay on top of the game. So I'll see you guys Monday at 1 o'clock, and I'll be putting the homework in as soon as I get it loaded up for you. Have a good day.